All right, so we're on camera now. That means we all have to be on our best behavior. This is going to be archived for the eternities. Space aliens in the future are going to watch these lectures and infer so much about society from the good questions that you ask. They'll say, man, students in West Virginia were intelligent. Asked all kinds of great questions, and boy, did they participate. Man, they'll be really impressed. So let's look at these announcements. Let me give you the handouts for today. The next homework assignment is already, of course, in the schedule. If you wanted to jump ahead in the semester, you can always do that by looking at the schedule for the semester. But I do point out a couple of things on here that I would like you to use. For example, the Colbert equation to solve for the F value on problem 4. And just so that you get a little bit of practice with it, is there enough copies of the notes if you need more? Oh, great, just head down. The Jane equation you can use on 5. Problem 26, we're going to, hopefully, if we've got enough time, look at an example that will inform the way you can solve that. And the reason being that it's an iterative problem, but you should set it up by hand and then solve with Excel using the Jane equation to solve for F. So we'll hopefully get a chance to take a look at that today, and that is due on Friday. Any questions about these announcements? All right. Well, there are several methods for finding the head loss in a pipe. This happened last time, didn't it? The Darcy-Weisbach being generally, for closed conduit flow, the most accurate among them. And the reason why it's the most accurate, of course, because the F value changes depending on flow conditions. It's not just some constant roughness factor that is ignorant of whether the water is moving fast or slow, the temperature of the fluid, or even what the fluid is. The F value is really smart in that it can take into account all of those things. And that's why the Colebrook and the Jane equation are so hard and complex to solve, is because there are a lot of different things that go into accounting for really how the boundary layer of the fluid, which is in contact with the pipe material, is leading to resistance as water flows through a pipe. So it's the most accurate, and it's the most flexible in that it can be applied to things other than water or to other temperatures. But finding F is another problem in and of itself. So it can be iteration within iteration sometimes when you're using the Darcy-Weisbach equation. Hayes and Williams you've seen before from a lab experiment last semester, although I don't know that we looked too much at what the limitations are. Strictly speaking, the Hayes and Williams equation is only valid for pipes with a diameter between 50 millimeters to 1850 millimeters. And so I don't think any of the pipes we used last semester were in that range. I think that they were all smaller than that. And so some of the deficiencies in the Hayes and Williams equation for calculating energy loss could be that we were out of range. Another interesting fact is that the Hayes and Williams equation was derived for sort of room temperature water, 16 degrees Celsius. And so when water is very warm, there are mistakes with the Hayes and Williams equation, and also when water is cold. Water flows through pipes underground at about 55 degrees Fahrenheit, which is going to be less than 16 Celsius. I don't know exactly what it is in terms of Celsius, but maybe 8 Celsius or so. 12.7. 12.7, okay. So there will be some variation in head loss when you're outside of this range of diameters, temperature, and velocity. But of course, it is definitely easier to use because the C values in the Hayes and Williams equation are constants. So here are a couple of different ways of seeing the Hayes and Williams equation in SI units and British gravitational units, or traditional units. The difference being this factor here in the front. And if you look in the equation packet that I've given you for the FE, they refer to it as a K value in front of there. And so rather than giving you two sets of equations, whether it's SI or BG, I think what they do is they just write the equation as the velocity is K, CH, hydraulic radius, SF, and then the K values they define for the two different unit systems. If you know the slope of the energy grade line, S sub F, let's say because you know the head loss that there's going to be, and you know the length of the pipeline. And why would you know what the head loss is going to be? Well, you know what the head loss is going to be if you know that there's some elevated tank, and you know the elevation, and then the water was running out of some open faucet. The head loss is going to be the elevation difference, essentially. There will also be the velocity head to take into account, but sometimes you know the head loss, and you want to find what will be the velocity through the pipe in response to that. So that if we had a higher tank, of course, the velocity is going to move faster. You know, if you elevate the tank, the C value won't change. The hydraulic radius won't change. But what will change is the S sub F. And remember, S sub F, well, all these markers are terrible. It's H sub F divided by length. And so elevating the tank is going to marginally increase the pipeline length, but what it's really going to increase is the H sub F, because you're going to have some additional elevation that's the driving force. And so the velocity will increase in response to that. It will come back into a new equilibrium when you raise the tank. The other way to look at the Hazen-Williams equation is its ability to tell you what is the energy loss for a known velocity, for a known pipeline length, known diameter, known friction. And so there are really two different types of questions that it gets asked in. If you have a defined energy situation and want to know how will the water respond, or if you know what the water is doing and you're curious to know how much head loss there is. Two sides of the same coin. Manning's equation isn't real accurate for closed pipes, but it's easy to calculate also for the same reason that Hazen-Williams, because the roughness coefficient N is constant with respect to flow conditions, with an asterisk next to that last statement, because sometimes when you are using Manning's equation and you're looking up an N value for a certain kind of material, sometimes they'll give you a different N value depending on the flow conditions. So, for example, you might have an N value for grass where the water is moving at a low velocity, or there could be a different N value for grass where the water is moving with a high velocity, because whoever put that table together knows that grass that is standing upright would give you a different amount of resistance to then when the water starts moving fast enough that it's pushing the grass over, then the N value will be lower. There will be less resistance. And so the N value doesn't really change as you're solving the problem, but sometimes you'd use a different N value depending on the conditions that are described in the problem statement. And we'll see that through the semester. Now, I know that I introduced you to Hazen-Williams equation last semester, and generally I don't do that in fluid mechanics. I gave you sort of a sneak preview, but what I don't remember is whether we did an example problem comparing the three different methods. I don't think that we did, but that's what we're going to do today. We're going to take a situation where there's a certain pipe, and we're going to calculate its performance using Darcy-Weisbach, Hazen-Williams, and Manning's equation, and see, relatively speaking, how accurate each of them is. This particular example, I don't think will ring a bell for you, right? A comparison of one pipe by the three different methods. Oh, did we really? Oh, well, yeah, I think the lab demo that we did was the same kind of idea. Right. Well, we're going to just take a quick look at this one and then move on to that iterative example that I want to show you today so that you can easily solve that homework problem. All right. So if this is a ductile iron pipe, we can go back to the previous table and see ductile iron has a range of C sub H values, but a typical value of 130, and if we were using an N value, it would be 0.013. And so that's what we used as this typical value, the given N value in the Manning's equation. And in the Darcy-Weisbach formula, of course, it doesn't give us directly an F, but we can find an equivalent sand roughness with the variable k sub s or epsilon, 0.26 millimeters. And we'll use that equivalent sand roughness to find the relative roughness of the pipe when we solve Jane equation. All right, so according to, first of all, the Hazen-Williams approach, the h sub f is going to be 6.82 times the length, diameter to the 1.17 power, velocity c sub h 1.85. So 6.82, the length here is 500 meters in pipe, 0.150 meters, 1.17 power. It's flowing at 1 meter per second, and the roughness coefficient of 130. Okay, so if we do it, then we end up with this first term here is going to be 31,385. I like to break it up into pieces like this because I find it easier to double check my work when I keep track of the intermediate quantities like that. So it is 3.85 meters of head loss. Okay, so if we combine and we compare that to how Manning's equation would see the situation. Remember, Manning's is great for open channel flow. So its core performance here, we won't hold it against the Manning's equation because this really isn't where Manning's equation is intended to be used. The n value of 0.013. So if we find the h sub f, 6.35 n squared L v squared divided by d to the 4/3. And that's a really strange version of Manning's equation. When we use Manning's equation for open channel flow, this is more of what it will look like. Or sometimes we'll have Q is equal to A divided by N. But what we've done here is rearranged Manning's equation to solve for h sub f. So this is sort of an unusual incantation of it. But we'll substitute in the nonetheless just to see. So 0.536 by 7.97 minus 2, 6.73 meters. So pretty big discrepancy between Hazen-Williams and Manning's equation so far. And I'm going to need the most amount of space for the Darcy-Weisbach equation, so I'll move over here to the other side of the whiteboard. Okay, remember that the first thing we need to know is characterize the Reynolds number. So that'll be the velocity times the diameter divided by the kinematic viscosity of the fluid. 1 meter per second times the diameter of 0.15 meters divided by the kinematic viscosity, 1 times 10 to the minus 6 meters squared per second. So 1.5 times 10 to the 5th is our Reynolds number. That puts us in the turbulent range. So we'll put that into Jane, which allows us to find the F value directly without any iteration required. Logarithm of the K sub s, 0.26 millimeters, divided by 3.7 times the diameter, 150 millimeters, plus 5.74 divided by the Reynolds number to the 0.9 power. Square that, all that goes over here. Okay, So 0.0240 is the F value. And if we substitute now that into the Darcy-Weisbach equation, each sub F is FLV squared divided by D2T. Then 0.0240 times the length, 500 meters, 1 meter per second, squaring that, divided by diameter to G. Okay, 4.08 meters. So the Darcy-Weisbach equation is the most accurate among them. But you can see there was maybe 2 extra steps we had to follow in order to use it. We had to find the Reynolds number, and then we had to find the F value before we could substitute it into the Darcy-Weisbach equation. So the purpose of that illustration is just really to, for a single pipe, show the range of values you could potentially get using these different approaches. So why do you think the Manning's equation overestimated? What do you suppose it is about Manning's equation that overestimated how much head loss there will be? It's hard to say exactly. The Manning's equation is often applied to an open channel, so that, most often it's used when the top of the surface isn't in contact with the water. And so it might be here that because the water is in contact with the entire pipe, that it's overestimating the amount of energy loss because there's a really long wetted perimeter. But the velocity here is relatively slow. 1 meter per second is a pretty slow moving velocity. And so it might be the combination of those two things. The fact that the wetted perimeter is higher than most of the situations where Manning's equation is used, coupled with the lower velocity, where Manning's equation was really calibrated and these n values were determined for typical flow conditions. So it's really all in the n value. If you assume a different n value, then in this case, since it's n value squared, let's say that you make a 2% change to the n value, then that's going to result in more than a 2% change in the head loss that you determined. It looks like it would be 4% since it's squared. So let's move on to something that's going to be more important to you in the immediate future, and that is an example where we find the pipe diameter needed using Excel. What I've done is I've adjusted one of your homework problems so that you're not seeing exactly the values that you yourself need to calculate, but the structure of the problem is identical. In the homework problem you're going to be facing due on Friday, they tell you the pump's rating in terms of horsepower. And so the first thing I want to point out is that you can convert between the horsepower of a pump and the H sub P, which is the head added by a pump with the formula that's shown there. The conversion being that 550 is the number of feet-pounds per second that are in a horsepower. And so in this problem, what we're going to do is we're going to convert, first of all, the horsepower of the pump into the pump head that's added. And we're going to try and find out what pipe diameter is needed for this situation. And the equation that we're going to use for the main solution is this one. And that is the energy equation and the Darcy-Weisbach equation combined together, solving for the diameter. And this equation that I've just put on screen is one that you saw in Lecture 5 last time. It's one that we used in the iterative process there. So it looks a little bit funny, but essentially all it is just the combination of the energy equation and the Darcy-Weisbach equation. So I'm going to switch to Excel, and okay, we're going to start with the problem where the horsepower of the pump is defined as 10 horsepower. The cast iron K sub S value, the equivalent sand roughness, that's something that you can look up in a table, or in a previous lecture we had a slide that defined the equivalent roughness, epsilon, which is equal to K sub, oh, PowerPoint. Why can't we get along? Okay, this K sub S value is from a table. You can look it up. The unit weight of water varies depending on the temperature. And in the problem that you're going to be working, they, I think, say the temperature of the water is 60 degrees Fahrenheit. So this is the unit weight of water for 60 degrees Fahrenheit. The kinematic viscosity for water at that same temperature, we can look up out of a table. Hopefully you kept your fluid mechanics book, because that has a nice fluid properties table in it. And in this example, we're going to be working, the flow rate is 1.5 cubic feet per second. I think in the homework problem they give you the flow rate in gallons per minute, but you can convert between gallons per minute and cubic feet per second pretty easily. I think it's 1.38, no, 0.138 cubic feet in a gallon, but you better double check that. Okay, so first of all, to find the pump head that's added, we just use this formula here to solve for H sub P. So it's 550 divided by the horsepower divided by the unit weight of the water. I'm sorry, times the horsepower divided by unit weight of water divided by Q. So you can see that I'm once again using that double divided by thing rather than parentheses. Hopefully that wasn't too confusing in the example I showed you in the recorded lecture, and maybe even before I showed you that this is equivalent to the same thing as if we'd said divided by this times that. Same thing. All right. The head loss, H sub F, that's written here is derived from the difference in elevation. It's solving the energy equation for the H sub F. So here, if we write the energy equation, Z1 plus V1 squared divided by 2G plus the pressure head is equal to Z2 plus V2 squared divided by 2G plus the pressure head at 2 divided by gamma plus H sub F. So in the spreadsheet where I've got H sub F listed here, what that really is all of the energy that there is at 1 minus the elevation at 2. And so in this flow situation, the energy, well, we've got a pump, so H sub P plus. So this is the energy equation for the flow scenario. It does include the pump term on the left-hand side. So the elevation difference between the two is 35 feet. And so what I'm saying is that H sub F is the 35 feet. It's HP minus Z2. So it's how much pump head is added minus the elevation at 2, assuming that elevation at 1, that water surface, is equal to 0. The elevation difference of 35 feet. Okay, so that's where this H sub F comes from. And G is a constant. The length is defined in the problem. Okay, so the first thing we have to do is type in the Jane equation. And by typing it in our reference format, that's going to allow us to copy and paste this solution multiple times. And I was telling you at the beginning of class that the Colebrook equation doesn't naturally guide you towards a solution. It doesn't like self-correct. but this will self-correct. We're going to put in some guess value of f, and then it's going to gradually get better and better. The guess will get better in each step. So remember that the lowest value of f, 0.008, would be the lowest value of f that you could see. In future iterations, rather than providing a guess, we're going to use the equation for f. The diameter based on, here's the equation for the diameter. Okay, so we'll use that equation. It is 8 times f times L. And anything that references up in this range, I'm going to anchor by pressing F4. If you press F4 after you do a cell reference, then it puts those dollar signs in there so that it will stay constant. And when you drag it down, it won't lose track of that. It's a little shortcut, pressing that F4 button. Times the flow rate squared divided by h sub f times g times pi squared. And now all of that to the 0.2 power. So I'm going to double check and see that everything is anchored except for the reference to f, because f is going to be changing every time I iterate the solution, but none of the other things are going to change. And so I'm just looking through the solution, and it seems like everything is anchored. Okay, so if that's the f value, this is the diameter that would be required. Well, shouldn't that be the end of the problem? We've just found the diameter. No, remember, that's just based on a guess of f. Well, if that was the diameter and this was the flow rate, what would really be the f value? That's what we're going to be finding next. And so the area would be pi times the diameter squared divided by 4. The velocity would be q divided by a. And then the Reynolds number would be the velocity times the diameter divided by the kinematic viscosity. All right. Well, if we have a Reynolds number, I'm going to copy and paste all of that. Copy, Control-C, paste, Control-V, except for I want to change one thing. I want to change the f value so it's not just this input guess that I did. I want it to actually be the formula, the Jane equation now. So equals 1.325 divided by the logarithm of k sub s anchored divided by 3.7 divided by d, the previous d, plus 5.74 divided by the Reynolds number, previous Reynolds number, to the 0.9 power. And now I'm going to have to, oh, I've lost track of how many parentheses I've got. I need to put in another square term there. Let's see. Okay, so closing that. Okay, square it at this point. All right. So what you can see is the f value now is based on the new diameter from the previous step and the Reynolds number that it would be if that was the diameter. So then this is going to calculate a new diameter based on this updated f value. This area will be based on the new diameter. This velocity is based on the new area, the Reynolds number, based on all this new information. And then all I have to do, I got to keep the spacing the same. Like there was one space between this first one and the next one. If I had 2 spaces, it would throw everything off. But if I if I keep the spacing the same, everything will work out fine. And you can see that the guess is changing. So the first guess was 0.43 feet. The next guess, 0.5393. Now it's not changing very much. What that means is it's naturally converging on the solution. The difference between my previous guess and this most recent updated value for the diameter, that's a pretty small change that it just did. And so this is converging really quickly. So I can Control-C, Control-V again, And the solution essentially is almost converged. There's hardly any change. I'll just do it one more time because it's easy. Control-C, Control-V, and now there was no change this time. And so the solution is converged completely. And so really the beauty that underlies that process is just that when you use relative references for formulas, then you can copy and paste multiple times, and then it will only look at the new value of what you didn't anchor. And so in my formulas for everything, what I didn't anchor was the reference to the F value. So my first one, this was a guess. And then this was using the Jane equation. And from there, it just fell into place really easily. And so then this is the diameter that's needed in order to get the 1.5 cubic feet per second with a 10 horsepower pump through the 800 feet of pipe that's described. All right, so that's the difference between intelligent iteration and blind iteration, is that just sort of intelligently converge towards the solution, whereas with the Colbert equation, we're just updating the values manually and kind of blind. It doesn't automatically fall into place like that. Any questions about the example?
So that one more problem that you said you want us to do with Excel, did you want us to like print out our Excel, but it's with it?
Yeah, what I want you to do is I want you to set it up by hand and then print it out by Excel. And so what you would print would be, it would be like just a printout of this. You know, this process that shows your initial values, your guess, how it converges.
And then like finish it like with our
We actually,
on paper.
it's really what you'd be doing on paper is maybe the stuff before that. You know, converting GPM to cubic feet per second, defining the variables would be done on paper. Solving the H sub P from horsepower, that sort of stuff. And so if we just take a quick look at the announcements one last time here. So you can really probably do most of those problems already. If you have any questions, feel free and see me during my office hours. Otherwise, I'll see you on Wednesday.